So let's look at what this least squares objective function is doing in pictures. So again, we have a two-dimensional input, and we're predicting something in R, which is this y dimension here. And so these red dots each are each a data point that we have. So for example, this dot here gives us a two-dimensional location in the x1, x2 plane, and the y value is the corresponding output. So we can represent this in 3 dimensions. Then we learn a hyperplane, or we learn a linear function of this, where we have, according to the previous slide, we have this sort of a function where d is now equal to 2. And that looks something like this. So we take x1, multiply it by a weight. We take x2, multiply it by a weight. So pretend that we have this point here. We take the x1 coordinate, multiply it by its weight, the x2 coordinate, multiply it by its weight, and then add the offset w0 to that, and we get our prediction, which is this point on the plane here. And the error of that prediction, if we're looking at this point, is equal to the length of this point to the plane squared. So that's the squared error. So we basically take each point, we drop a line parallel to the y axis to the plane. That length is our error of our prediction. We then square that value, sum up those values, and that's our total error. And so what least squares is trying to do is it's trying to find an orientation for this plane so that it cuts through the data in a way where the sum of the squares of these lengths are minimized. Okay, so thus far we have our data pairs xi, yi of the measurements in RD and their corresponding responses that we're hoping to predict in R. We've hypothesized that there's a linear relationship between xi and yi, meaning that we can multiply xi, the jth dimension of xi, by some weight wj, add up those multiplications, include our offset w0, and then we have some error and we have an approximation of yi. And our goal now is to minimize the sum of the squared errors, which means that we're trying to minimize the sum of the squares of these epsilon i's, the number that we have to add in order to get this to become an equality. And of course, that's simply just taking the output and subtracting our regression function, which is, in this case, is equal to this. So that's our error. We square that value and then sum up those errors, and that's our objective function. So this is what we're trying to minimize. This sum is what we're trying to minimize in W0, W1 through WD. So before we do this, let's ask whether we can use some nicer math notation in order to represent this in a way that's easier to work with. When we look at the notation, what we're going to do is just something very simple, and often this is done. This is done either in your code or if you're reading papers where these things are explained. Is what we're going to do is we're going to take the intercept and add that to the dimension of x. So we're going to extend x from being in RD to being in RD plus 1, where we take each point xi and we add a 1 to the first dimension of it. And now we can interpret that first dimension as being multiplied against w0, because in that case, every single function evaluation for each of these xi's will have w0 times 1, which is the offset. Then we're going to take each of these vectors xi and put them along a row of a matrix, call that capital X. So that's what we have here. We have the first column is all equal to 1 to account for the offset. And then each feature vector is put along a row of the matrix from the second column through the d plus first column. And now we're going to put the weights in a vector that's also in d plus 1. So we take each of these weights and we put them into a vector, and that's what we're going to call W. And so notationally, we're always going to think of these vectors as column vectors, meaning if I write xi, and this is a vector, then I'm assuming that, for notation purposes, I'm assuming that this is a column vector. So for example, we could, for the ith person, we could fill in those values with their age, their height, weight, their income, and those could be the inputs that we're using. And the set of n vectors are going to be stacked row-wise into a matrix. So when I write capital X, I'm assuming that each row corresponds to one observation. So the vectors xi, the vector xi is transposed to become a row vector and put along the ith row of this matrix X. And also, an assumption that we're going to make is that features are treated as continuous valued. That's not necessarily going to be the case, but it's a simplifying assumption we're going to make. And we're going to assume that we have more observations than we have dimensions. And we'll see why that is in a minute. OK, so let's look at the least squares objective function in vector form using our vector notation. So this is the original objective function that we have. We have the output minus our approximation using linear regression. That's the error. We square that, sum up those squared errors, and that's the objective that we're trying to minimize in W0 through Wj. And so using vector notation, we've simply taken this term here and written it as a dot product between the input xi and the coefficient vector w. This is simply equal to this according to our definitions previously. And so now we have our output is approximated by the dot product between the inputs and the coefficient vector w. We square the error, sum it up, and we have that this is equal to this. So now our goal is to minimize this objective function in the vector w. And we see immediately why it's nice to have this vector notation. What that means is we simply want to take the gradient of the objective function with respect to the vector w and find the point at which it's minimized, meaning the point at which the gradient is equal to 0. And if you think intuitively what that means, if this is the function L and this is w, the gradient, the point at which the gradient equals 0 is the minimum of that function, which is this point here. So we're looking for that minimum. We're hoping that we can analytically solve this. We're hoping that we can find the global minimum. In this simple case, all of those things are possible. So we take the gradient of the objective function. We find that the gradient of L is just the sum of the gradients of each observation and set that equal to 0. When we take the gradient, we remember that the gradient of this function here is equal to this. We solve for w and call that the least squares solution, indicated by a subscript ls. So we take the gradient of the objective, we get this term here. We want to find the value of the vector w at which that is equal to 0, and we can solve that to obtain this solution here. So let's just quickly look at how we could write this in matrix form. So this is introducing some notations that will be used throughout the course. Vector forms, matrix forms. It's very convenient to use these shorthands. So taking this vector representation and putting it into a matrix representation using the previous definitions, what we have is that we can stack the values of yi into a n-dimensional vector because we have n observations. So y now is an n-dimensional column vector of all of the outputs, and we're approximating that vector with the matrix x times the vector w. So x, remember, is an n by d plus 1 matrix, and so the ith row of the vector y, the ith dimension of y, is approximated by the ith row of x times the vector w, which is simply what we have written here. except now we can write that as the error vector. So we take the vector y and subtract off the vector xw, which is our approximation of the vector y. And then we take the dot product of those error vectors in order to represent the sum of squared errors. So this vector here is the vector of errors of our approximation, and this dot product then gives us the sum of the square of those errors. So now if we work with this function and we take the gradient with respect to w again, we find that we have this as being the gradient of the objective. We again set that equal to 0, and we find the least squares solution, which now has this nice matrix vector form. So just as a refresher, to quickly give a review of what matrix, the matrix vector product versus a sum of vectors times a scalar, how do these things relate? So remember that if we have a matrix X transpose here, so in this case, because each xi is along a row of the matrix X, when we transpose that, each xi now is a column of X transposed, times the vector y, which is the stacked outputs of each observation. We simply take the first dimension times the first column and add to it the second dimension times the second column all the way to the nth dimension times the nth column in this way. So this is how we think of a matrix vector product. It's taking each column of the matrix X, multiplying it or scaling it by the corresponding value in the vector y, and then adding those up. And so that's simply what these two notations are doing. And similarly, when we have matrices multiplied by each other, in this case X transpose X, what we can think of that as is taking the first row, or the first column of the left matrix times the first row of the right matrix, which is this outer product, xi transpose, and then adding those all up. So we get x1 transpose all the way to xn transpose. We add those outer products up, and that's what this equality is simply saying. So basically we have two notations for the key equation for least squares linear regression. We have that the vector w that minimizes the sum of squared errors, the least squared solution, can be written as either the inverse of the matrix formed by taking all of the inputs and putting them along the rows, as well as adding a column of ones to the first column, taking that product, inverting it, and then multiplying it by this matrix vector product, and so the result is a vector of dimension d plus 1. Or similarly, we could write it this way. It's saying exactly the same thing in different notation. So now that we have the least squares vector, this is the solution to our problem. This is the value of the vector w that minimizes the sum of squared errors. What is the first thing that we immediately think that we would want to do with this? Well, immediately we think we want to make predictions. So in real life, we have the data, the pairs of inputs and outputs. We learn our model, and now we want to use that model to predict the output that we don't know for an input that is coming to us. So for example, in the Old Faithful example, we learn our model from the data that we've collected. We then measure the amount of time the geyser is erupting. When it finishes erupting, we have that amount of time. We put that into our linear regression model to get a prediction for how long we're going to have to wait to the next eruption. And then we show that on a sign so that people know when they should come back. So basically what this is saying is that given a new input, x new, we take our least square solution and we predict the output that we don't get to observe as the dot product of the input with our least squares vector. And so this is our approximation according to our linear regression model of what we think the output's going to be for the new input. I've worked out the math and everything worked out fine, but we've kind of skirted some potential issues, and one of those is that we actually can evaluate this equation in order to find the least square solution. And what that really ultimately means is we're assuming that we can invert this matrix X transpose X. And that's not always going to be possible. So when do we know that it's not possible? So we know that this matrix X transpose X is not going to be invertible when it's not full rank. So we need the matrix X transpose X to be a full rank matrix. And so we immediately ask, well, when is that matrix full rank? And so the answer is that when we look at the n by d plus 1 matrix X, it has at least d plus 1 linearly independent rows. And so what this means is that any point in Rd plus 1 can be reached by some weighted combination of d plus 1 rows of X. So this is one condition for that matrix X transpose X being full rank. So we'll return to this later, but obviously we can immediately say that if the number of data points is smaller than the dimensionality of the problem plus 1, then we can't do least squares, because it's not possible to find d plus 1 linearly independent rows of X, because there aren't that many rows of X in this case. So what we need, the kind of takeaway is that what we want for least squares to work is the number of data points to be much greater than the dimensionality of the problem. So we want the matrix X to be tall and skinny. That's not a guarantee that it's going to work. We'll discuss more later about when it still might not work, but we're well on our way if we have many more data points than dimensions of our problem.